So welcome back. In the previous video we talked about Fréchet derivatives. This notion of a derivative is a linear transformation between vector spaces. In this lecture we're going to specialize to the setting where these vector spaces are finite dimensional. So functions from Rd to Rk for certain d and k. And we're going to relate this concept of Fréchet derivatives to partial derivatives, to gradients and Jacobians, which we all know from calculus. And we're going to see that, well, knowing how to compute partial derivatives is not in itself sufficient to compute the Fréchet derivative, even to know that f is Fréchet differentiable. However, if these partial derivatives are all continuous, then we can get the Fréchet derivative very easily. Okay, a recap. We have a function between two Banach spaces v and w with their respective norms. When we say that, we have x naught belonging to u. When we say that f is Fréchet differentiable at x naught, we mean that if we write f of x naught plus h, that's equal to f of x naught, right? X naught plus h, x naught, plus this bounded linear map applied to h, plus a remainder term. And remember that by definition, the remainder term is something that when you divide it by the norm of h and send h to 0, this remainder term should go to 0. Right, so there's a slight simplification when to this definition when v equals Rd, because in this case we know that all linear transformations from v to w, no matter what w is, they're bounded. So there's no issue. I mean, you don't need to prove that a linear transformation from Rd to any other vector space is bounded. It's automatically bounded. So, so you can forget about this word in the definition. I mean, of course, not in the general setting. But when v is equal to Rd, this is something you don't need to require. It's superfluous. Right? But that doesn't help us much. I mean, this is just saying, okay, there's one last thing that you need to check, but we still don't know how to compute this Fréchet derivative, right? So in the previous class, I gave you a hint of how to try to compute a Fréchet derivative in a general setting. You can start by computing these Gâteau or directional derivatives, and then try to find the Fréchet derivative from them, because there's a relationship, right? So let us now note a similar thing, but perhaps even more specific for the case when v is equal to Rd and w is equal to R. So it's function from Rd to R, or for domains in Rd to R. Okay, let's at least try to get a look. Let's try to find out what the Fréchet derivative should look like. Right, so we have the same formula as before. But now notice that, well, our Fréchet derivative is a linear transformation from Rd to R. That's a linear functional. And we know that all linear functionals over Rd have the same form. They all consist of taking a vector, a fixed vector, and saying, well, the linear functional is computing the inner product with this fixed vector. Meaning that if I have this linear functional, there has to be a vector here, the gradient, that we all know. Well, we're going to see that's a gradient, right? So, but in any case, what we know from general theory is that there exists a fixed vector such that if for any age, if I want to compute the value of my linear functional applied to age, that's just the inner product of age and this fixed vector. And I've already let the cat out of the hat. So I've already said it's a gradient. So how do we know it's a gradient? Right? Well, how do we compute the coordinate? So we have this mysterious vector, right? So how do we compute its coordinate? So all we know is that its inner product with fixed vectors age is related to this linear transformation. So let's use that knowledge. So the ith coordinate of this mysterious vector is just its inner product with the ith canonical basis vector. Of course, this is for all coordinates I from 1 to d. Now, as we notice, this is just this representation theorem saying that The inner product corresponds to the partial derivative, to the Fréchet derivative applied to this vector. And then using, when we related Fréchet derivatives to Cateau derivatives in the previous class, we proved that such an expression is always a limit like this. Oh, wait, I had a 0 plus here, I mean t positive, but it's really the same proof to get this inequality. Now, what we have over here, we're looking at a function f at x naught. When you change the ith coordinate, and then you're taking the derivative, pretending that all coordinates but the ith one are fixed, and you're treating this as a function of a single variable, a single real variable. Of course, when we do this, we get the partial derivative. I mean, that's sometimes notated as df, dxi. I always use this notation d sub I. So this is a partial derivative. If for whatever reason you've never seen partial derivatives in your life, that's a definition. But not only the definition will be important for us, but also the interpretation. The interpretation being that when you take a partial derivative in the ith variable, you're treating f as if all the variables but the ith variable are fixed, and therefore you have a function from R to R. You have a function of a single real variable, which is just this ith coordinate that you're changing. So this interpretation is going to be very handy for us when we prove theorems about this thing. Well, actually, I have already proven a minor result about this Fréchet derivative, which is this. So we figure out that the coordinates of this mysterious vector, or the gradient, right, they're given by the partial derivative. So we've seen that if we know that f is differentiable, or Fréchet differentiable at x naught, then we have this vector of partial derivatives. It has to be well defined, right? So all the partial derivatives at x naught exist. And moreover, we have this expression that's just a definition of the Fréchet derivative, right? So because this is equal to df x naught applied to h, we have this expression f of x naught plus h is equal to f of x naught plus h inner product with the gradient plus a remainder term, which I recall goes to 0 when divided by the norm of h, and h goes to 0. Now this is very nice. So it tells us that we can try to reverse engineer the statement and say, okay, if I want to compute the Fréchet derivative of a function from Rd to R, I know that if the Fréchet derivative exists, it's given by the gradient vector in this precise sense here. And I know how to compute the gradient vector. If I know any calculus, I just compute the partial derivatives, right? But there's something missing, which is that even if a function has partial derivatives in all variables, it doesn't mean that it's Fréchet differentiable. I mean, I'm not going to repeat the example. That's the example we saw in the previous class, right? In the previous video, where we showed that there are functions that have directional derivatives in all directions and nevertheless fail to be continuous, right? At 0. They have all partial derivatives at the point 0, the origin of R2, but they fail to be continuous at this point. And because of that, we know that a function, I mean, it's the same thing, or you can go back and check it out. That function has all partial derivatives, or both partial derivatives, right? Because we have only 2, d equals 2. So it has both partial derivatives at 0, but it's not differentiable at 0. So there's no converse to this result. It doesn't follow, I mean, it's not true that if you have partial derivatives, they're differentiable. However, there is a partial converse that's very useful. And here's its statement. So now I'm assuming that I have an f, right, defined over an open set in V. And V is Rd, sorry, right? So that's... And the important assumption is that the partial derivatives, they exist over the whole set U, and they're continuous. So it's not just that the partial derivative exists at a point, it exists at all points, and moreover, it's a continuous function of the point. Right? Then, it turns out that f is differentiable over the whole of U, of the whole set U, and for any point, I can compute its partial derivative by the formula that I showed before. that partial derivative, sorry, not the partial derivative, the Fréchet derivative is given by the gradient. As we know, it must be, right? So the challenge here is to prove that it's Fréchet differentiable. If it is, so I know that this is true. But of course, we're gonna use the fact that the gradient exists and is continuous to prove this statement. Right? Why is the gradient continuous? Well, I mean, the gradient is made up of coordinates. All the coordinates are continuous functions. Therefore, the gradient is a continuous function of the point x0. But we're not going to use that directly. I mean, you're going to use it in the proof, but let's see how it goes, right? So before I present the proof, let me point out what the challenge here is. The challenge is this. So as we saw before, directional derivatives and therefore partial derivatives, they tell you what happens to the function if you change one coordinate at a time. So if I move from here to here, or if I move from here to here, I know what happens. So, and the Fréchet derivative is different. So if I change coordinates in an arbitrary way from the origin, it will give me some information. It gives me, there's a fine approximation, so there's something that's trickier than with directional derivatives. I mean, there's no preferred direction. There's no coordinate system. I mean, there is a coordinate system, but there's no preferred coordinate system when you talk about Fréchet derivatives. So you have to approximate f by an affine transformation no matter which direction you move, so to speak. And all we know is that the partial derivatives exist, so we can move in the direction of each coordinate axis, but not in other ways. So we'll have to use the fact that the partial derivatives exist and are continuous to be able to overcome this obstacle. And the way we're going to do it is we're going to look at f of x0 plus h, pretending not that we move directly from x0 plus h, but that we change the coordinates of the vector one at a time. Okay, how do we do this? First of all, it turns out to be convenient in this proof to use the infinity norm. And I mean, that's going to... So basically, what does a ball look like in the infinity norm? It's just a box, right? So I'm drawing here in 2 dimensions. Sorry, there's no x's here. This is x0. So it's just a box, or hypercube if you want, with side length 2r. So this is its center at x. So this is r, this is r. And as we'll see why it's convenient soon, right? So, okay. Because U is an open set, I know that there is an open ball in the infinity norm centered at x0, right? So if x0, of course, is a point of U, just like in the previous slide. So I know there's a box, an open box around x0 that's entirely contained in U. It's protective bubble, but this time the bubble is a cube, not a sphere. So of course, what that means is that if I take a vector h with infinity norm less than r, I know that x0 plus h belongs to U. And okay, so, and we know, okay, take such an age, right? So, an age, we know that as any other vector, we can write it in terms of the canonical basis vectors. Meaning, if I take the sum of ith coordinate of age times ith canonical basis vector, I get age. As I said, we have to look at what happens. We want to compute f of x0 plus h minus f of x0. But I need to change the coordinates one at a time, right? So when I go from x0 plus h, to x0 plus h, I'm changing all the coordinates of x0 potentially at once. So I want to do it one at a time. So I'm going to define a sequence of vectors that are going to be kind of age if you change one coordinate at a time. So you start from the 0 vector, and the jth vector is, you take the sum that defines age, but you only add up to the jth coordinate. So if you think about it, say that age is like let's look at 2 dimensions, just to make life simpler. So age sub 1 is a vector that has the first coordinate equal to 1 and the second coordinate equal to 0. And I mean, in general, you're gonna age j is a vector that has the j first coordinates equal to those of age and the remaining coordinates equal to 0. But the important thing for us is this formula here, right? So age d is just age because you have added up everything. Age 0 is just 0. Therefore, f of x0 plus age minus f of x0 is this difference. It's the same thing. And here's the crucial step. I can write as a telescopic sum. Right? So when we add these guys up, we know that we're left with the last guy, which is f of x naught plus hd, minus the first guy, which is f of x naught plus h0. So it's exactly this. And now I've achieved what I wanted, which is to move kind of one step at a time from x naught to x naught plus h by changing only one coordinate. Right? Now, the factor in the cube, right, that we are using the infinity norm is going to be useful now, because of course, if I want to write this, I need to make sure that these x naught plus h j belongs to u for all h that I consider, right? Well, for j equals 0, that's obvious because you're just looking at x naught, and x naught belongs to u. For j equals d, that's also obvious because we assume that h belongs to, has infinity norm less than r. But the intermediate guy is an important thing because it's that each one of these vectors has norm at most that of h. And why is that? Because remember, what is age j? That's the vector age, except that I make the last few coordinates equal to 0. So the first few coordinates agree with those of h, and the remaining ones are 0. Therefore, its infinity norm, its largest coordinate in absolute value, cannot be larger than that of h. So we have this inequality here. Meaning that if we know, right, so if we have this, then we guarantee not only that age x naught plus h belongs to u, but x naught plus h j belongs to u for all j. And moreover, as I mentioned, right, so we can move from x naught plus h j minus 1 to x naught plus hj by changing a single coordinate. So we have a change like this. Okay, what's the upshot of all that? Now I'm going to use crucially this fact that when I'm only changing one coordinate of f, I have basically a function of one real variable. Okay? So what do we know about functions of one real variable? Well, it's a differentiable function because the jth partial derivative exists. It's actually a differentiable function with continuous derivative because we're assuming that all partial derivatives are continuous. But we don't need that, right? What we need is the mean value theorem. The mean value theorem tells me that if I take a function of one real variable and I compute it at 2 points, a and b, then the difference of f, b, and f of a is equal to the, right? So that's equal to the difference between b and a times the derivative at some point in the middle of the way, right? So this delta j, the important thing is that it lies between 0 and 1. It's actually strictly between 0 and 1. So, of course, I'm not computing at a, b, I'm computing at a point, so you can say I'm computing at a point that's this guy, and then I add h, j to jth coordinate. So the difference is h, j, the jth coordinate of h. So I should be careful, right? It says h bracket j, that's the jth coordinate of h. So that's this guy. And then I need to compute the derivative at some intermediate point. And I'm just writing, okay, so I'm taking age, jth coordinate, and multiplying that by a number between 0 and 1. That's the intermediate guy. Right, so we're very close to what we want. Let me notice that I would very much like to have this equal, or approximately equal, to the partial derivative of f of x naught times h sub j. And why is that? Because I'm going to add these guys up, and when I add these, I get the inner product of h and the gradient. So that's what I'd like to have. So basically what I'm going to show is that because the partial derivative is continuous, if h is very close to 0, then this is very close to this guy. Okay? But let's do that carefully. Okay, so that's what we have over here. So that's another way of writing the same result. So f of x naught plus h sub j minus f of x naught h plus 1. That's jth coordinate of h times the partial derivative computed at a point x naught plus an h tilde j minus 1. That's just a name I gave to that vector that showed up here, right? So that's h tilde j minus 1 is equal to x to h j minus 1 plus theta j minus 1 jth coordinate e sub j. That's the definition. But the important thing for us is that this vector is also bounded in infinity norm by the norm of h. And why is that? Because, well, the j minus 1 first coordinates of this vector are equal to the coordinates of j. The jth coordinate is the jth coordinate of h multiplied by a number between 0 and 1. So it's less than the jth coordinate of h in absolute value. And, sorry, should be less than or equal to. And the other coordinates are 0. So this is going to be crucial, right? So the fact that we have this is crucial. Because now I'm going to write this as h jth coordinate times the partial derivative of f of x0. And then I have the remainder term here, which is just this guy. Right? And crucially, when h goes to 0 in infinity norm, then this aj minus 1 tilde goes to 0 as well, because remember that its norm is bounded by the norm of h, right? So that's what we argued before. And therefore, because the partial derivative is continuous, so delta j of h goes to 0 by continuity of the partial derivative. So very importantly, delta j of h is going to go to 0 when h goes to 0. And now I'm basically done. So if you buy this, which you should, right? Because I'm saying, okay, when h goes to 0, this guy goes to 0. Therefore, this difference goes to 0. This difference here goes to 0 because the partial derivative is continuous. So if you buy that, bear with me, we're almost done. Because now we have we wrote this difference as this telescopic sum. The telescopic sum we rewrote like this, and now we have here the thing that should appear if this is a Fréchet derivative, and this should be the remainder term. So let's quickly argue that that's the case, because, okay, what happens with this term here when I divide by the norm of h, infinity norm? Well, let me just notice that this term, right, it's a sum of d terms. So I'm just going to say, well, it's a sum of j equals 1 to d, h sub j, delta j h, all absolute values here, norm of h infinity. And notice that these things here, the ratio of jth coordinate of h by the infinity norm is always less than 1, less than or equal to 1. Therefore, right, because the infinity norm is just the largest value of these guys, so that's less than j equals 1 d delta j h, absolute value, and this converges to 0 just by the continuity of the partial derivative. And what have we shown? We have shown that if you like to write it in another form, f of x0 plus h is equal to f of x0 plus h inner product with gradient plus a term r of h that when divided by norm of h goes to 0 when h is small, right? So hopefully you can see why the inner product showed up here. It didn't say that explicitly, but it's just that I have the sum of jth coordinate of h times jth coordinate of the gradient here. And that's the inner product of h and the gradient. And also, hopefully you can see why this goes to 0. Well, that's not quite an inner product, right? Because, well, it is an inner product. But the important thing is that it's an inner product of h with a vector that has coordinates equal to delta j of h. So if you like, we're using Holder's inequality here for the infinity and the 1 norms. And delta j of h, this vector of coordinates delta j of h goes to 0 because each delta j of h has this very specific form, which is partial derivative of x at x naught plus a vector that has a norm less than or equal to h minus partial derivative of x naught. Partial derivative is continuous, and therefore delta j of h goes to 0. And that's the end of that theorem. That tells us that if f has partial derivatives, right? F goes from u containing Rd to R. If it has continuous partial derivatives over the whole of u, then it's also Fréchet differentiable over the whole of u. And we know that we can compute the Fréchet derivative like this. Applications of this theorem, well, now you know that basically 99% of the functions that you looked at in your calculus class that are functions of several real variables with real values, well, 99% of them anyway, they're Fréchet differentiable because we can compute the partial derivatives and we can see that the partial derivatives are continuous. So that's good. Finally, we know how to compute Fréchet derivatives, right? That sounds like an accomplishment. It actually is a pretty big accomplishment. Okay, so now we're going to switch to a slightly more sophisticated case. So this should be, RD to RK. Now, I'm not going to do this case in a lot of detail, and it's going to be clear why. Basically, it's this. So, okay, we know, we've seen it several times before, that when you have a function from Rd to Rk, you have these coordinate functions, right? So f of x is a vector that's f1x up to f dx. Sorry, I should have used a different color here. Right, so we have this thing. These are the coordinate functions. We know, for instance, that f is continuous. If and only if each coordinate function is continuous. Now, the exercise is to show that f is Fréchet differentiable if and only if these guys are all Fréchet differentiable. And then to show that the Fréchet derivative of f is vector valued, but the Fréchet derivative comes from the coordinate functions. Well, how do we do that? Well, that's just an exercise in writing things down in terms of linear transformations and whatnot. I mean, that's, again, it goes back to this very basic fact, which is that convergence in Rd, in Rk, sorry, here should be K, right? It's the coordinates, right? So convergence in Rk is equivalent to coordinate by coordinate convergence. So if you understand that and you put some effort, you should be able to prove this, okay? But let's believe this exercise, because now we know a very powerful theorem that says, okay, first of all, if I want to write down this Fréchet derivative, right, so dfx naught is a linear transformation from Rd to Rk, linear. Therefore, it should be representable by a K times D matrix. And you can get this matrix from the formula in the previous slide. It's the Jacobian matrix. What is this matrix like? Well, it has K columns and D rows just because it represents a linear transformation from Rd to Rk. And if I look at the ith row, the jth column, that's the jth partial derivative of the ith coordinate of f. So basically, if you like, you have f. So on each row, you put the partial derivatives of the first coordinate and then the second coordinate and third coordinate. So these are the coordinates and these are the partial derivatives. And then, of course, we have a generalization, right? So as we noted, differentiability from Rd to Rk is essentially differentiability from Rd to R. So we have a theorem that says that if this Jacobian matrix is defined over the whole of U continuous, then f is Fréchet differentiable. So it's the same theorem as before. There's nothing new here, right? Because we're only talking about differentiability coordinate by coordinate. So if you know that all coordinates are differentiable, then we know that f is differentiable. And it's equally useful in the sense that most functions we see in calculus from Rd to Rk they have coordinates. They all have partial derivatives that are continuous, and therefore we know how to compute their Fréchet derivatives. We know how to write down explicitly the matrices corresponding to their Fréchet derivatives, which are these Jacobian matrices. And so now that we know how to differentiate functions in the simpler case, which corresponds to calculus, we're going to finish this video. Next time we're going to come back and we're going to consider functions between more general Banach spaces. I mean, there's no kind of general theory that allows you to compute all partial derivatives, or sorry, to compute all Fréchet derivatives, but we're going to see some examples that are especially important and actually applicable in different settings. Yeah, that's it for now. Thank you.